Okay, folks, welcome back. Let's continue our afternoon session. Our next speaker is uh, Tadahisa Funaki from BIMSA, and he'll talk about conservative dynamic PO2 model on the whole plane and its reversible measures. Let's give him a warm welcome.
Thank you very much. It is working. It is working. Okay. So thank you very much for kind introduction. Also, I'm very happy to present here. And also, thank you for coming. So my talk is about the conservative. So maybe in the next page, about the conservative. And also, I use the non-conservative dynamics as a tool, and it is a conservative dynamic P2 model, which is a kind of the singular stochastic PD. So it has a shape written here. So we consider on R2, so two-dimensional equation, and we have a phi. Phi is a scalar value, and it is a function of the t and x, and we have a bi-Laplacian term, and also some nonlinear term, which phi is a fourth order polynomial. Therefore, p prime is a third order polynomial. So we have a certain nonlinear term, and also we add some function of the x here, and then we have a gradient of the Gzai. Gzai is so-called space-time Gaussian white noise defined on R2. But we have two independent space-time Gaussian white noise. So essentially, we have this one. This is called a conservative dynamic P2 model. And also, just look at this one. So this is called a non-conservative P2 dynamical P2 model. So this one is simpler than this one. We have a Laplacian phi. So this leading term is a heat equation. We have a nonlinear term and also some spatial inhomogeneity and the noise. Xi is a noise. And Xi is again the space-time Gaussian white noise. Actually, Xi, the regular, so it is essentially the heat equation. But Xi is so bad. This is a distribution valued stochastic process. Therefore, the solution is actually, even we drop the nonlinear term, the solution is not function value. It is a distribution value. We only have a distribution value solution. So we have a cubic term. So how to define the cubic term? That is a difficult point. So in this sense, the PD, this stochastic PD is called a singular stochastic PD. Situation is the same for this conservative one. We put the Laplacian here, and also actually we put the square root of the minus Laplacian here. Then it is more convenient to write in this way, but originally it is a square root of the minus Laplacian. We put the minus Laplacian here compared to this one. We put the minus Laplacian here. Then we put the square root of the minus Laplacian in front of the noise. So then actually this one is very well studied. Maybe I will show you in the next slide. But however, this is not well studied. And from my viewpoint, I work on the so-called hydrodynamic limit. To work on the hydrodynamic limit, so I will touch later, we need to study the conservative system, not the non-conservative system. So this is a conservative system because if you, so roughly saying, if you integrate this phi is a function of t and x, and also randomness omega. But if you integrate in x, then you have a Laplacian. So if you integrate over R2, then by the integration by parts, this term cancels, in fact, because of this. If you integrate over the whole domain. Also, you have a derivative. Therefore, if you integrate over the whole domain, this is a bit heuristic. The integral of phi, which is heuristic, which may diverge, but and the time derivative of the integral of the phi is 0. That means spatial integral phi is constant in time. Therefore, this one has a conservation law. On the other hand, this doesn't have, because here and here you don't have derivatives. But this dynamics and this dynamics is well studied in physics. And because there is a fluctuation dissipation relation, if you have some operator here and square root of its operator, then the invariant measure, or the what happens at the time t goes to infinity, that is studied by the invariant measure, but the invariant measure doesn't change. That is so-called fluctuation dissipation relation in physics. Therefore, this dynamics and this one should have the same invariant measure. In fact, this one, or maybe this one, is a gradient of this one. So this is the measure on the defined on the space of the phi, and this is called the so-called sometimes Lagrangian or the Hamiltonian. But if you take a gradient of this one, gradient of this one gives a Laplacian, maybe minus Laplacian, and the gradient of this one gives a p prime, and you have something like so. Derivative, then just you pick up lambda. So this is essentially the gradient flow. So this is the gradient flow corresponding to Hamiltonian defined in this way. And the fluctuation dissipation relation suggests this measure, if it is well defined, should be the invariant measure under this dynamics and this dynamics, or the maybe also reversible measure under this dynamics. I expect. And especially if you put a lambda here, if lambda is a harmonic function, Laplacian lambda disappears. So, okay, so I write in this way, but if you add some harmonic function, lambda tilde to this part, lambda plus lambda tilde, and lambda tilde is a harmonic function on R2, then it disappears. Therefore, these measures, so this, if we can define that this dynamics, then these measures should be the invariant, not only just mu of lambda, but also lambda plus lambda tilde, and lambda tilde is a harmonic function. So this one should have plenty of the invariant measures. On the other hand, for this one, only we cannot put this one because we don't have a Laplacian in front. Therefore, this one we expect maybe a unique invariant measure, but this should have plenty of the invariant measure. That is also the reflecting the nature of the conservativeness of the dynamics. So we want to discuss the existence, uniqueness, starting with the existence and uniqueness property of this dynamics, and also the what is the reversible measure, and also what is the invariant measure for this dynamics. And actually, we use this one, which is simpler, as a tool to study this dynamics from the viewpoint of the invariant measures. The motivation is actually in the physics paper, Hohenberg and Halperin, and they call the non-conservative one model A and the conservative one model B. So, and also it is called the time-dependent Ginzburg-Landau equation. So in physics, it is quite natural dynamics, and both model A and model B are studied. But from my viewpoint, since I want to study the so-called hydrodynamic limit, this conservative one is quite natural to study. Okay, so okay, and also the non-conservative one is introduced by in physics Parisi and Wu. It is quite well known as the model of the stochastic quantization. And as I explained, SPD1, first one, as a conservation law. And maybe I already explained it. Also, maybe we can condition due to this conservation law. And actually, my real goal is to study the hydrodynamic limit later. I started to study, but it is not finished. But hydrodynamic limit is a problem. So like deriving the Navier-Stokes equation or the Euler equation from the microscopic dynamics, it is similar. So hydrodynamic limit in probability theory, it is a space-time scaling limit leading to a certain nonlinear PDE by a local equilibrium and averaging under the local ergodicity. So this is called the hydrodynamic limit. So in the classical case, local equilibrium is a local Maxwellian distribution. Say starting from the Boltzmann equation, it passes under scaling local Maxwellian distribution. That is the equilibrium distribution. So, but if the equilibrium measure is unique, then this is trivial. We cannot get any nonlinear PD. Therefore, we have to study some system with a conservation law. So the second one is not real. So everything shrink down to the single point. So it's not interesting from this viewpoint. So my real goal is to study the hydrodynamic limit for this conservative dynamic P52 model. So before studying this, we have to establish the uniqueness, basic facts for the dynamics. Now, actually, a long time ago, I studied P51 model, 1D case. In this case, I did not explain, but to define this term and also this one, so because the phi is a distribution, then the cubic power of the distribution is not well defined. We need something so-called renormalization to define this term and also this term. Because especially the noise is very bad. Therefore, the solution is still not a usual function, but a distribution, only the distribution. Therefore, for the invariant measure, this is also, so we have to define mathematically rigorously, but anyway, this is not a usual function, therefore we have to introduce a so-called renormalization for this term. Okay, so but in the 1D case, actually phi is a usual function in the not R2, but R1. Okay, so in that case, we don't need a renormalization. In that case, I already proved the hydrodynamic limit starting from this SPDE in the 1D case, or in the higher dimensional case, regularized version. That is, and in the Hamiltonian, we replace this higher order differential operator. Then instead of Laplacian, we have a minus Laplacian to the power m. Okay, so here I replace so gradient to the power m. Then instead of Laplacian, we have a higher order differential operator. Then if this order is high enough, then the solution is actually becomes the usual function, not a distribution, due to the so-called Schauder effect of this differential operator. In that case, I already studied a long time ago the hydrodynamic limit for this SPDE. If 2m is greater, so m the power, this one is greater than 2m is greater than d, then the solution phi is the usual function, space variable. Okay, so if m, so just Laplacian phi, in that case m is equal 1, therefore this is 2. And if you consider 2D case, then this condition is violated. Therefore, this means that this is the critical case. If it is equal, then it is critical. And if m equal 1, then we take a Laplacian, then solution is not really in the usual function space. Therefore, we need a renormalization. That is what I want to discuss today. Okay, so I just pick up so many references for the non-conservative case. Non-conservative, maybe there are more, but it was started, I think, by the Plato and Tobishi 2003 on the torus case, and then Martin Heiller and Gubinelli and others introduced a new theory around 10 years ago. And the 3D case can be studied using these new technologies. And also Lekna 2 and 2 studied on and they, I think they proved the uniqueness of the invariant measure on the torus. And Murat and Weber discussed on the R2, but these are all non-conservative cases. And they don't put a lambda, therefore lambda should be constant. But so many papers, and easier in a sense, still, but still easier compared to the 3D case. And the 3D case is also studied by several people. And so many people studying this direction for the non-conservative SPD. On the other hand, conservative case, which I'm interested in, is not well studied, I think, and only which I know is by Michael Lechner, Yan and Tzu, Ronchan Tzu, and they study on the bounded region, bounded torus T2. To study the hydrodynamic limit, it is necessary to go to the infinite volume because we will start from the finite volume, but eventually by scaling, we should know some properties on the infinite region. So that is the reason why we want to study on the R2, not the bounded region. Okay, so they proved that so many things, global uniqueness of the invariant measure, and so on. They proved so many things. Okay, so now I want to come to the, so this is a summary, very short summary of the result we obtained with, so I didn't say, but I'm working with Chizan in the BIMSA, and also Hansen start sitting over there at the BIMSA, and also Binxie at the Hsinchu University. Sorry, I didn't tell the beginning. So we construct the measure, which I wrote in the first page. Heuristically, we will construct this measure as a limit of the first. First, we define on the bounded torus, but the size m. M eventually goes to infinity, but first, this one is well defined. This one is well defined because starting from the Gaussian measure. So maybe you can look at it again. So we have this Gaussian part. So you just forget these terms. So then this is a quadratic function. Then we have uniform Lebesgue measure that this and this together with this one can be understood as a Gaussian measure, but with a mass 0, but we will add the mass. But then we have to say to the something to this term. But anyway, this is the Gaussian measure, which is actually called the Gaussian free field on the R2. But actually, it is more easy to add the mass term. Therefore, we start with the mass term. M square is a mass term. And then this is a Gaussian measure. This is already supported on not the usual function space, but a distribution space. Then we define this. We can define this one. In the 2D case, it's not so deep. It's actually well known. In the torus case, we need some renormalization based on the big decomposition, big powers. Then we can define it is not already. And then we put a lambda. Lambda is a spatial inhomogeneity, but we can add this term to this measure. And this is well defined once lambda is actually the function. Then even if phi is not usual function, but this is well defined. Then we can define this one this way. So by using the renormalization on the finite volume, then we will show that this is compact or the relatively compact as the probability measures. Then we can let pass to the limit as the size of the torus m goes to infinity. Then we will get this measure. That is the first result. Then for the dynamics, we will start giving the local well-posedness. We can solve the SPDE on the R2 starting from this one. So this is the Bezos space, and the alpha is any positive. So alpha is very close to 0, but it should be positive, but it can be taken very close to 0. And then we should introduce some weight. On the R2, we need to introduce a weight. And the PQ, so this is LP in space, and LQ in a sense, a Fourier mode. That maybe in the, we can say, it's a LQ in the differential operator sense. So then that defines the Bezos space, and but alpha should be positive. We cannot take alpha equals 0. So it's a distribution space. Then we will have a local well-posedness. That means until some time, which we call the survival time. Until survival time, we can solve this SPD. And then once we can construct this reversible invariant measure, then if the initial value is taken under this measure almost surely, except the measure 0, we can show the global existence of the solution. And also the reversibility. But for any lambda tilde, which is harmonic function, so we have plenty of the invariant measures. And also we can define the conservation law on the whole space R2. I will explain later. Okay. Okay. So this is a rough explanation of our result. And the notation, maybe I already said that weighted Bezos space. We need some, due to the noise term, maybe there is some fluctuation as x goes to infinity. Therefore, to control that, we introduce some weight. And the weight should be integrable. So we consider on the R2, this sigma greater than 2 means that it is integral. And we will use several notations on the bounded torus. And also we use the lattice approximation. Therefore, we also consider lattice approximation of the torus with the size epsilon. We start, so to identify the invariant measure for the conservative case, we compare with the non-conservative one. Then if you go to the lattice, then the SPDE is reduced to the finite dimensional SDE. And then we can identify the invariant measures for the non-conservative and conservative. For that purpose, we go to the lattice approximation. And to distinguish, we put the non-NC, that is a non-conservative and conservative. If we consider on the lattice, on the torus of the size m, so we put m and n. And yeah, maybe I will explain in the next page. We consider that we just pick up the linear term from the SPDE for this phi. That is called the so-called Ornstein-Sternberg process. And we consider two types of the Ornstein-Sternberg process, which is the first one, this script one, has the initial value, which is the same given by 0. But if the initial value is taken to be 0, then we simply write z. But this is so singularity of the SPDE is coming only from this OU part. Okay, so maybe I can show you the next slide. So we decompose phi t. So this is already considered by the Plato and the Vichy 2003. So in this case, we just pick up. So in the conservative case, we just pick up the linear term of the SPD. So just coming back. So we are considering, we want to consider this one, but we just drop the this nonlinear term and also this term. Then you have a bi-Laplacian term and the gradient of the exact. But the singularity comes from this one. So we pick up this linear term. So this is the bi-Laplacian term and gradient of the noise. So we consider this one. Then we consider phi t as a perturbation on this z. Z is actually the distribution value. And then we consider the rest. We denote by y. And the rest, then y should satisfy some equation. But anyway, this was introduced by the that's a long time ago. Then in the 2D case, z covers all singularities, and yt is much better. But in 3D case, this method doesn't work. But in 2D case, this works well. So we are considering only in the 2D case. Then we decompose phi t into two terms, and this is in a sense easy to treat. But although z takes a value in the distribution space, but it is easy because it is actually the Gaussian process. And then the nonlinearity is put here. Then just expanding the equation, the one, then we have something messy terms. But first we can solve this one, and then we put a z here. Then z is a very bad distribution value. Therefore, we introduce weak product or the renormalization to this term. Then we can define this one. Then actually we can solve this equation in a proper setting. Okay, so this is the plateau as the idea, and this essentially works in our situation. And this is the whole program which we want to develop. So the strategy for that one. So we actually, as I said, we start from the discretized version. That is the lattice approximation. So we consider finite. So we want to study the whole space R2, but first we consider on the finite volume, but with a periodic boundary condition. But to identify the invariant measures of the both conservative and non-conservative, we go back to the lattice approximation version. Then for this one, it's not difficult because SPD becomes just a finite dimensional stochastic differential equation. Then we can write explicitly what is the invariant measure and what is the reversible measure. That is actually quite well known for the, especially for the gradient system. Then we want to pass to the limit. So we have to prove the convergence of the process and also convergence of the invariant measure. So invariant measure is defined on the lattice first. Then we have to prove that this one is compact, or the relatively compact at the family of the probability measure. The first M is fixed. Then that is called the tightness. Then we need some energy inequality for the SPD. Actually, to show the tightness of the compactness of these measures, we introduce energy estimate. Then this gives a good moment estimate for this one. That implies the compactness. Then we can pass to the limit as epsilon tends to 0. Then we can have some measure. Then this measure is actually already studied for the non-conservative case. So by passing to the limit, maybe the uniqueness of this object is not shown just by this compactness. However, already on the torus, the uniqueness of the invariant measure for non-conservative cases is shown. Therefore, we can identify what is this one. But especially lambda is a constant case. But anyway, by using this non-conservative dynamics, we can identify this one. Then we repeat something similar. Then again, we show the energy inequality for this object. Actually, the energy inequality for this one is actually very hard. Therefore, we use this dynamics to show the compactness of this object. So non-conservative one is much easier. Then by using this dynamics, we can show the compactness of these measures, then we can pass to the limit. So the uniqueness for this one, for each lambda is unknown. So because just we show the tightness, that is the compactness. So we don't know. So here it is unique, but for this one, it's still not well studied, I think, even for the non-conservative case. So, but anyway, in this way, we can construct this Gibbs measure, so-called the Gibbs measure. And then we can, by using this measure, actually, we can prove the survival time becomes plus infinity by using this information. And then we have a global well-posedness for this dynamics. That is what the whole strategy we want to discuss. Okay, but anyway. Okay. Okay, so, but okay, so lambda is the inhomogeneity in the space is taken from this space, but we assume slight regularity in alpha. Sorry, in the space, because we have a coupling between the lambda and phi, but probably it's not really needed. Only what we need is some LP property. Maybe we can relax this one, but anyway, we at the moment we assume this regularity for the external field lambda inhomogeneity in space. Then because we consider on the torus, therefore we should approximate it from the torus. Then we just restrict on the this then we extend periodically to the outside. That is called the lambda. Then this converges well. Okay, this is not. Then the discrete conservative and non-conservative dynamic, but a discrete one. So which this is the first step which we discussed. So we replace the Laplacian and the gradient by the discrete Laplacian and the discrete gradient, and also the Brownian motion. So this is the Brownian motion, but this is defined from the original space-time Gaussian white noise. Okay, so this is a vector value. So this is a R2 value, the vector value. So this is a two-dimensional Brownian motion for each x. But if x is different, those are independent. Okay, so that we start from this one, and then we need the renormalization already at this level because we want to get the limit as epsilon tends to 0. Therefore, even at the lattice size, we have to define this renormalization properly to get a limit as epsilon is infinity. So 0. Sorry. Then okay, so we have this decomposition. Then okay, so essentially we have this convergence by taking the renormalization term properly. So lattice, this is defined on the lattice, but it is extended as a step function. Sorry, maybe I didn't say, but it is extended step function. So this is defined only the lattice point, but we can extend it as a step function and on the continuous torus. Then we can prove this converges to the solution of this one. So this we prepare to identify the invariant measure of this one, and this one is the same. And then we can identify the invariant measure of this one through this non-conservative one. Okay, so we establish the lattice approximation in this way. But these are just the technical things. Then we want to show the compactness, that is the tightness. This one, so the torus size is fixed, But the lattice size, so epsilon, we want to essentially go, epsilon goes to 0. The lattice size epsilon want to go to take to 0. Then to show the compactness of this one, we apply the energy inequality for the dynamics. To show the tightness of the measure, we use the dynamics. This is actually well used recently for many other settings. But we take a same strategy. So we use the dynamics to show the tightness of this one. So we compute the LP energy, then we have just this one. And so y part is, so z part is bad, but the y part is nice, and it is actually lives in the LP space, not in the distribution space. Therefore, we can compute, and also this epsilon level is of course okay, but in the limit also it stays in this space. So therefore, we can compute in this way. Then this is bounded, and we pick up this term. We pick up this term, so you divide by capital T. Then maybe to avoid the time 0, then we take from 1 to T plus 1. And then this one, if it is invariant, then this one is equal to this one, because this is invariant under the time evolution. Then just integrate by in t, the length t divided by t, therefore it is equal to this one. So then this one is given by the energy inequality. Then you divide by capital T, then essentially you pick up some constant coming from this one. I think this one contains t, therefore some uniform constant. And then other terms anyway goes to 0. Therefore, this is bounded, uniformly bounded in epsilon. That shows the compactness of the. Okay, so sorry, maybe y term gives, and also z term we have to consider on the distribution space. Therefore, in total, phi is the sum of the y and z. Therefore, in total, we have to consider on the space of the distribution, Basel space. Then this one. So this implies the compactness, or we can pass to the limit. And then this is the invariant measure, both for the conservative and non-conservative. Okay. So and also reversibility can be shown starting from this one, then by just taking. And as I said, the uniqueness is important, in fact, to identify. So by compactness, by tightness, we can take a subsequence which converges to some measure, but maybe this may not be unique. However, for the conservative dynamics, especially lambda constant case, the uniqueness of the invariant measure for the conservative dynamics, that was shown by Reknatsu and Su. And also, I think this is Hendrik Weber. Okay, so these people already showed. And even, I think they proved the spectral gap also estimate for this bounded region case. But so we use this uniqueness. Therefore, we don't need to take a subsequence. This one itself converges to this one based on the analysis of the non-conservative dynamics. Okay, so in this way, we have some information for the reversible measure. Then we do the same. Now we have this one. Therefore, we want to pass. So we want to consider on the whole space. So this means that we consider on the m times t2. That is the torus with the size m. Then we want to let m go to infinity. Then we again apply the same technique. We use the dynamics to show the compactness of the measure. So we can repeat something similar what we did for the lattice approximation. Since y part is nice, actually we have this estimate by using the dynamics. Then especially we pick up this one. This one is bounded by some constant, essentially, or maybe this goes to 0 as t goes to infinity. Therefore, this gives some compactness of the tightness of this measure. Then we have this estimate also. And not only the tightness, but also this one is used to construct the global solution. In fact, the survival time, we introduce maybe in the next slide, survival time is plus infinity to show that we use this information also. Okay. So then the local well posedness. So this is also used, say, by similar to by Martin Heiler. But this is well-known method. So we consider then for y part, so we introduce a fixed point argument for the y part, and then what we have to show is that this one should be the fixed point for this map. Then we can construct some fixed point, but that is only local in time. So we have a survival time, t survival. And then up to survival time, we have a solution that we can construct starting from any initial value taken from this Bezos space. And also, we can see that survival time is plus infinity or finite. If survival time is finite, then this norm should diverge. Also by this fixed point argument tells. If survival time is finite, then the limit as t goes to infinity, t goes to this survival time, the norm considered in this Bezos space, but the continuous function as a taking value in this Bezos space should diverge. That is also shown. And also, so also we constructed on the torus, but this one converted to this one up to the survival time in some sense. So we can also the convergence of this process defined on the torus converted to the this one the constructed in this way on the R2 converged in this space up to this time. Improbability. Improbability means the norm is defined in this space. Okay, so we have such kind of result for the local solution. Then for the going to the global solution, global well posedness, we use this estimate. We use this estimate. We prove that this estimate for the tightness, but we use also this one. And based on this estimate, we can prove this is if survival time is finite, then because this shows some boundedness of this norm, therefore this stays bounded. So this is a contradiction because if survival time is finite, then it should be plus infinity. So, but this is only almost surely with measure 0. Therefore, we can prove the global existence only at the moment, only almost sure, almost all initial value under this measure, almost sure under this measure. And then we have a unique solution of this SPD that we can prove. So at the moment, we cannot extend to the all initial value taken from this Bezos space. So, but anyway, slightly weaker sense, we can prove the global well posedness for the our dynamics, conservative dynamics on the and the reversibility can be shown just by the reversibility and then just taking the limit. Okay, then conservation law. Conservation law, I just integrate over R2 at the beginning, but it doesn't have a meaning. Therefore, we have to integrate over the bounded domain, and we divide by the volume. Then we can prove this quantity exists. But we need some cutoff, but it's a bit technical. But for phi is for phi, for the solution, this quantity exists. Then conservation holds in this sense. Therefore, the canonical measure, that is a conditional probability, because this is constant in time. Therefore, we can condition this measure by this conservation law. That is also the reversible measure or the invariant measure for this process. And as I said, for the any harmonic function, these measures are the invariant measures. That also can be shown. Okay, so this is the remark. So we consider the energy inequality for non-conservative case, and we use the non-conservative dynamics. But it is more desirable if we can introduce energy inequality directly for the conservative dynamics. But it turns out very difficult, actually. In the, say for example, we should, so instead of the LP or the L2, we should consider the H minus 1 to cancel one Laplacian in the conservative case. So it is quite natural to consider the H minus 1 norm. Then we should, on the R2, we should introduce some weight, sigma of X, to control the Y. Then we take a time derivative of this quantity and the evolution of this SPDE. Then this kind of the norm is actually under this well studied for this is a singular integral. Then it is called a Calderon-Zygmunt theory for the with a weight. That is also well studied already in the PD group, and also one weight estimate, so sigma, and on the right hand side the same weight appeared, that is a Muckenhaupt estimate, that is also well studied. And two weights estimate, that is we want to bound this with another weight, that is called the two-weight estimate, is also well studied for the fractional integral operator. So this is the kind of fractional integral operators. And also Kato-Ponce commutator inequality is also well studied, and with the weight is also studied. But we tried, but now none of them didn't work. So we finally gave up to work directly and to derive some useful energy inequality for the conservative case. Okay, so this is the reason why we consider the non-conservative dynamics. And once we can show that, it is also known that once we can show the so-called strong pair property for this one on the R2, then maybe conditioning the tail sigma field, maybe we can replace this one, because the strong pair property means some continuity. Therefore, almost all can be dropped by using some continuity once we can show the strong pair property of this one. But maybe it's not so direct, because I once had the talk by Susen Zhang. So he considered a much easier SPD, but on the whole domain, a strong pair property doesn't hold. Therefore, maybe we have to be careful to show. Maybe our next goal is to show this one. But maybe Martin Heiler introduced asymptotic strong pair property. Therefore, maybe we will try to study this property maybe the next to extend this almost to remove this almost sure, almost all condition to all. Okay, this is what remarks. Then actually what I want to do is the hydrodynamic limit for this singular SPD. Maybe I have maybe 5 minutes. Okay. Okay. Okay, so we consider the SPD, the conservative SPD on the bounded region, n times torus, that is enough, but n eventually goes to infinity. Therefore, to study the infinite domain, R2 is important to study this problem. Then, actually, we consider the phi is the solution of the SPDE defined on this space. Then we introduce a space-time change. That is the diffusive scaling. So in time, we have n squared. In space, we have n. So this is the usual diffusive scaling. Then I expect this one converges to the solution of this nonlinear PD. Because in the one case and also the some regularized case, we have this result, and also Fried and Razakanlo a long time ago proved hydrodynamic limit, not the continuum one, but a discrete conservative Ginsburg Landau equation. That is just the discretization of our SPDE on the d-dimensional torus with the size n, but a discrete one. And he derived this nonlinear PD even under the phase transition. Actually, the phase transition is this one. So for lambda, so we take a lambda is constant, then we have a spatially homogeneous on the translation invariant measures. This is not unique for our SPDE. Then for this one, we have a density that is the integral of the phi field. This is distribution, but we can define this quantity. Then if rho is not uniquely determined from lambda, then it is called a phase transition. And I expect, for this model in the 2D case, Grimm, Jaffe, Spencer approved that there is a phase transition. If polynomial term is taken like a double well potential. Therefore, in our case also, we have, in this situation, we have a phase transition. However, Proudhon proved that even if there is a phase transition, we can derive this nonlinear PD. So I expect my conjecture is even for this singular stochastic PD case, maybe something like this kind of nonlinear PD can be derived. But we have to do several things. First one is the characterization of the grand canonical, the canonical measure also. And then the space phi is very bad. Therefore, usually to characterize the Gibbs measure, we use a DLR equation, Dovruchin-Danforth-Ruehl equation. But for bounded region, we need some boundary condition, but phi is very bad. However, we can pick up some certain boundary term, which is so-called the domain Markov property. We take a massive case, then I expect we can define this one. And the canonical Gibbs measure is also we further conditioned by the conservation law. Then we can define these things. And what we have to prove the invariant measure of this our dynamics on R2 are this canonical Gibbs measure. To prove the hydrodynamic limit, we have to prove this kind of statement, and also the just averaging effect, ergodic property, and this Gibbs measure should be shown also. And then I expect the relative entropy method that is introduced by Baradan and others. I checked, and then at some point it works. It works well, but the most difficult point is still we have to prove this kind of statement. This invariant measure should be the canonical Gibbs. That should be proven. This is this looks, and also ergodic property. Maybe the time is so. This is the summary. So we discussed the existence of the dynamics and also the reversible measures, invariant measures, and then I just touched very briefly the hydrodynamics. Thank you very much.
Thank you. Question?
Yes.
To prove this reversibility for the invariant measure, is that part required and needed for the tightness proof?
Yes.
Is needed?
Yes.
Oh, okay.
So we prove the tightness by using the dynamics, especially non-conservative dynamics.
More questions?
So if you replace the weak renormalization by another renormalization, for example, you shift the weak constant by finite constant, that essentially changes the lambda, I guess. Would that affect the hydrodynamic limit?
So what do you mean? So the renormalization term you change some constant?
Yeah. So weak renormalization is one way to renormalize the 542. There
that
are,
I don't know actually. I don't know. Well,
yeah.
so but then the lambda changes.
Yeah.
Okay.
I don't know if we do a finite shift of lambda, would that affect the hydrodynamic limit?
I don't think so, because
the same.
in the equation there is no lambda. Actually. We start with sorry, maybe I didn't say very clearly, but we start without lambda, but lambda appears just to characterize. So there is no lambda. So we start without lambda. This equation on the torus side n. For that, then invariant measure is not unique, but we pick up only the lambda constant because the invariant measure, which is a shift invariant, appears. Therefore, lambda doesn't appear in the dynamics. However, yes. So, is that okay? Maybe.
At some point, you mentioned the strong failure property. Could you use a result from Martin error and Mattingly, or you cannot apply
so
it?
that we want to expect, but
you expect to be able to use his results?
No, because they study, I think,
a finite volume. So you want to look at
extend to the infinite volume.
Infinite volume.
Not direct.
Okay, so
but the idea is something similar, maybe.
Okay, but
expect, you. But
yeah.
So as I said, he pointed out in the actually the initial value term is difficult in a sense. In the infinite volume term, there is it doesn't hold. The strong failure property actually doesn't hold.
Okay.
Even the very simple SPD case. Therefore, we have to be careful. Good.
Yeah. Thank you.
Any more questions? Okay, if not, let's thank the speaker again. Back at 3:30.